The other thing about the lone pair is because it's involved in delocalization. In the resonance hybrid, the dipole was affected in the sense that the dipole pointed away from the nitrogen in that direction. So the dipole in this molecule went like that. Now in pyridine, we have a slightly different situation. I mean, for all practical purposes, it looks very similar. It's a nitrogen in a 5-membered ring, and it's also aromatic. But in the nitrogen, what we find is that that lone pair is in the plane of the molecule. That is, it's perpendicular to the p orbitals, like these p orbitals, and as a result, does not get involved in delocalization. The result is that the nitrogen's lone pairs are permanently pointed in this direction, and because it doesn't delocalize, we find that the molecule has a dipole moment that points towards the nitrogen, so it actually points in that direction because the nitrogen's more electronegative and because of the lone pair on that nitrogen. You can also see that in the resonance structures for the nitrogen, several of the contributors have this negative charge on the nitrogen as we delocalize the electrons. And that's another reason why the dipole moment is relatively large, pointing towards the nitrogen. Because that lone pair isn't involved in resonance, that what we find is it can act as a base. Now, its pKa is around 5.16. That of a saturated nitrogen, an sp3 nitrogen, is about 11.2. This is expected because of the hybridization of the nitrogen, right? sp2 is more acidic than sp3. And that's that whole, we talked about this a long time ago, but that whole argument of percent S character of the atom. And so, as you would expect, pyridine can form pyridiniamine. Pyridiniamine, because it acts as a base, is a stronger acid than what you would find for a saturated amine. The other implications, so far we looked at it, it has a dipole moment that points towards the nitrogen. It acts as a base, and it can also act as a nucleophile in some reactions. And so it can be a nucleophile with methyl iodide to form this pyridinium ion. Or methylated pyridinium ion. It can also react in an electrophilic aromatic substitution reaction. Now, if you remember, for pyrrole, there was a definite preference for addition in the 2 position of the ring. For pyridine, there's a definite preference for having addition in the 3 position. So really it's meta. If you think about the preference, it's meta to the position of the nitrogen. And then for pyrrole, it's ortho in position to the nitrogen. Now, one of the things that we learned about pyrrole is it's more reactive than benzene. And the reason it's more reactive than benzene is because the lone pair of electrons on the nitrogen serve to introduce electron density into the ring and cause it to be more reactive. When we talked about substituted benzene, electron donating groups tended to be ortho-para-directing groups, especially if it had the lone pair. And so we see similar behavior for electrophilic aromatic substitutions of pyrrole, but we also see it in pyridine. The reason we see it in pyridine is because nitrogen is an electron in this structure, is an electron withdrawing group. Because in its resonance structures, it's more electronegative and can pull electron density out of the ring. The lone pair that's on the nitrogen can't actually contribute electron density to the ring because of its position in the plane of the ring. So the consequence is this nitrogen, its role in the ring is to slow the reaction down and direct substituents to the meta position relative to the nitrogen.
To understand why substitution takes place in the 3 or meta position relative to the nitrogen, you have to look at all the intermediates. And the bottom line is that when you do substitution in the ortho and para positions, you get relatively unstable intermediates as one of the contributors. So here's an unstable intermediate, and here's another unstable intermediate. And it's unstable because you put the positive charge on the more electronegative nitrogen atom. If you look at substitution in the meta position, what you find is the positive charge can skip around and misses the nitrogen in all the contributors. And so the result is overall the meta intermediate is lower in energy than ortho or para, and so substitution takes place at the 3 position. Having said that, it's important to also recognize that having the nitrogen in the ring makes pyridine relatively unreactive compared to benzene. And pyridine being less reactive than benzene wouldn't be so much of a problem, except it is also further deactivated by most of the reagents that are used in electrophilic aromatic substitution reactions. That is, if we use acid, this will protonate and become even more deactivated. And it's very difficult for pyridine to add substituents under normal laboratory conditions. In terms of relative reactivity, it's something between the reactivity of a single nitro group or 2 nitro groups on the ring. Pyridine, substituted pyridines can undergo nucleophilic aromatic substitution reactions for the same reason that they don't really undergo electrophilic aromatic substitutions very well. And that is because the nitrogen is able to pull electron density out of the ring. If you have a leaving group at the 2 or the 4 position, similar to nitro-substituted benzene rings, what you can get to happen is you can get a nucleophile to attack at the position of the leaving group and then have the leaving group leave during the reaction. It's helpful to look at the structures, resonance structures for pyridine. One would be, for example, like this. And you'll see that there's positive charge at the 2 position. And then one more resonance structure that's important to look at is this one, where you have positive charge now in the 4 position relative to the nitrogen, like this. There's actually 2 lone pairs on this nitrogen. So, and then one more, you get, again, another ortho substituted, or ortho, or 2 position carbocation. So, that being said, the reason nucleophilic aromatic substitution reactions work on benzene with nitro substituents or on pyridine is that when the nucleophile comes in on a benzene ring, its attack, which has to come from the top, is usually blocked. And as a result, like in benzene, because there's a pi cloud above the ring, the nucleophile can't attack easily and get past that pi cloud. But putting the nitrogen in the ring for pyridine, for example, or a nitro group outside of the ring, these are strong electron withdrawing groups. we can have nucleophilic attack take place. So I should probably put it at the bottom. We can have nucleophilic attack take place even though it's partially blocked by a pi electron cloud. The more electron withdrawing groups you put on the ring or in the ring, ortho and para to the leaving group, the faster the reaction will take place. We can also analyze the intermediates. And so if you do a two-position substitution, what you notice is you can put the negative charge on the nitrogen, which is more stable. If you put if you put it in the 3 position, what you find is the negative charge never actually makes it to the nitrogen, and so there's no more stable structure in any of these. And the same thing that you get in the 2 position, you get in the 4 position. You're able to put the negative charge on the nitrogen, which makes it a little bit more stable. When you go back, and if you're comparing it to these structures, you recognize that in this structure, the nitrogen doesn't actually have an octet, and putting the positive charge and depleting its octet is very unstable. Okay, so the trick is, though, for this to work, you have to have a leaving group. So let's say you have 2 substituents, like a bromine and a methoxy group. Well, the bromine is a much better leaving group than the methoxy group. So the nucleophile will add at this point here, and then the bromine leaves to leave you with the amine on the ring. Similarly, you can do a chlorine versus a methyl group. The chlorine's the better of the 2 leaving group, so that's where you get the substitution taking place. If you had a ring, for example, it looked like this, and you reacted with NH2 minus, you would only get substitution of this chlorine because the meta position is partially blocked by the electron cloud. And so the most likely product for this would be to put the NH2 in that position, leaving this chlorine unsubstituted. Now, the reactions of side chains, which were covered earlier in this chapter and in previous chapters, all can take place at side chains on pyridine. So you can do bromination at the benzylic carbon. You can do oxidation to a carboxylic acid. Under these conditions, this gets protonated, right? And so there's a number of, and oh yeah, another important one is if you do an NH2, you can also modify, do a diazonium salt and use this as an electrophile, or you can add water or to get pyridine, or you can use a mild reducing agent, like, for example, how to do this down here. Well, let me do it here, actually. Mild reducing agents here, like H2PO2, and you can just completely remove it altogether, and what you'll form is this. Okay, so there's a lot of different things that you can do also do the same reactions that you can do on benzene rings. One of the interesting features of alkyl substituted pyridines is that if the alkyl group is in the 2 or the 4 position relative to the nitrogen, what can happen is you can deprotonate the alkyl groups. So it could be a methyl group, or it could also be, for example, an ethyl group. But that carbon adjacent to the ring can be deprotonated, because when you do that, the electrons can eventually be delocalized onto the nitrogen. So, for example, just to see the resonance structure, the similarity, if I put one in the 2 position relative to the nitrogen, then what can happen is you can deprotonate it. And you can deprotonate it with something like, for example, sodium hydroxide. But just like enolate reactions, if you want to force it to be 100% deprotonated, you'll have to use a much stronger base. But this negative charge, just like it does in this structure here, right, the negative charge gets distributed onto the nitrogen, like this. So here's the thing. When you can do this, one, it acts like an enolate, but it could also act as a nucleophile. Okay, so here's examples of each of those behaviors. This is alkyl substituted pyridine in an aldol condensation type reaction. So you remove the proton from the methyl group. Again, it's got to be in either the 4 or the 2 position. You bring in your aldehyde, benzaldehyde in this example, and then it can attack. Eventually, what you end up with is the aldol product, not the condensation product. But it turns out that, hang on, let me get this drawn. Oh, it's just O minus in this case. Like this. Because it will sit between 2 aromatic rings, the extended conjugation of the system makes this dehydration, the loss of the oxygen, a lot more efficient. And so you end up being able to dehydrate this without actually doing anything else. In fact, it's hard to stop it from dehydrating because of the stability that's gained by conjugating the entire system. Here's another interesting example. You have 2 methyl groups in this case. Again, this is in the 3 position. This is in the 2 position. The methyl group in the 2 position is the more stable enolate in essence. It's the more stable or the more acidic hydrogen. Contains the more acidic hydrogens. So once you deprotonate it, then what you can do is you can bring in an electrophile like an alkyl halide for methyl bromide, for example, and you can alkylate this position relatively easily if there's a nitrogen in the ring. There are a number of biologically important nitrogen heterocycles. Of the amino acids, we have proline, tryptophan, and histidine. And histidine within its structure has a ring, nitrogen-containing ring that contains 2 nitrogens known as imidazole. Imidazole is aromatic, and one of the things interesting about imidazole is it has features of both pyrrole and pyridine that we've seen. It has a pair of electrons. Let me go back to this drawing here. There's a pair of electrons on the nitrogen here, which aren't involved in aromaticity. And it's got a pair of electrons here, and that pair of electrons is involved in delocalization to make the imidazole ring aromatic. So that aromatic portion of the ring has a pair of electrons that are part of the pi cloud, which gives it 3 pairs of electrons, and it has another pair over here which aren't involved in aromaticity. And so these electrons are not basic, but these electrons are basic. Here are some of the resonance structures of imidazole, and what you should notice about the aromaticity of this compound is based primarily on this pair of electrons. This pair of electrons that's here never actually is involved in delocalization. So in all of the structures, that pair of electrons stays outside the ring, whereas this pair is delocalized inside the ring. It leaves a positive charge on this nitrogen and a negative charge at times on this nitrogen. So there's a positive here and a negative charge here. So if you look at the resonance hybrid for imidazole, it looks something like this. I didn't mean to draw a double bond there. Let me just do this. And then nitrogens at the corners, and then delocalization inside the ring. A hydrogen on this side. partially positive here, and then a partially negative here, as well as negative, partial negative here, and a partial negative here, and a partial negative here. So that gives imidazole a very large dipole moment pointing in this direction. The dipole moment is about 3.8 dBi. This is a unit used for measuring dipole moments again, which is roughly twice the polarity of water. So it's actually very water soluble. Most organic compounds, if you remember, are not that water soluble, but imidazole is readily soluble in water. Imidazole also has two different pKa's. So the protonated form of imidazole has a pK of about 6.8. Imidazole itself has a pKa of about 14.5. So it's similar, again, to water in terms of its acid-base strength, but you can deprotonate imidazole. Like this. And again, this pair of electrons is not involved in the delocalization for resonance, so it can sit outside the ring. And then we have our three pairs still in the ring to provide aromaticity. And so this pKa, if I remember right, is around 14.5. Water, if you remember, is around 15 or so. Okay, so it has two pKa's. The one pKa is relatively low, near 6.8. And if you remember when we talked about a lot of the reactions involving nitrogens, how there's an important catalytic point in the middle pH range, imidazole is actually involved in a lot of biological reactions as a proton donating or receiving agent. So one of the places we see imidazole, as I mentioned earlier, is in histidine. Histidine is the amino acid with the imidazole ring in it. One of the things that can happen to histidine is it can be decarboxylated. That group can be removed, and then you get histamine. And you're probably familiar with the term antihistamine. Histamine bonds to a receptor and triggers our allergic responses. And so what organic chemists, pharmaceutical chemists did was decided that they would create a compound that would mimic the structure of histamine, but not trigger the response of the receptor. So basically blocking the receptor site and not allowing histamine to actually cause the allergic response. And so the earlier compounds that were created, Benadryl and chlortrimeton, you can see clearly some of the features that are the same. This is meant to be like a tail that inserts into the receptor. But then the rest of the molecule is designed to block the action of the receptor and block any histamine from entering. The problem with these two drugs is, even though they're effective, is that they also can cross the blood-brain barrier. So if you think about your brain, it's essentially surrounded by a nonpolar membrane. And so the types of molecules that can be transmitted to your central nervous system are those things that are nonpolar. And so Benadryl and chlortrimeton were two nonpolar. And so what they had to do was they had to have some polarity to the structure in order to try to keep it from crossing the blood-brain barrier. So that's why you see functional groups like this, and this added positive charges like this, for example, and then these larger, there's a polar section in here. Here you have the large polar region, and then you have this kind of polar region. This allows it still to block the histamine receptor, so they're still antihistamines, but keep them from crossing the blood-brain barrier. It turned out that histamines were also responsible, a different receptor in the stomach. So same compound, different receptors, were responsible in part for overproduction of acid in your stomach and leading to ulcers. And so that one of the early drugs created for that was Tagamet. Tagamet is generically known as cimetidine. And you can see, again, some of the structure is mimicked. And some of the structure is not. And the idea is to block that receptor to keep other keep histamines from entering and triggering that response. And so you can kind of go through all of these structures and kind of see, sometimes you can't see it, what's similar about the structures to the actual natural agonist for the receptor. But if you model these things, it turns out a lot of times if you do molecular models of these things, it's the shape of the molecule that's important, so you can see spaces in the molecule that have similar shapes. Another place we see nitrogen heterocycles is in DNA and RNA. And the bases the heterocycles, which we call the bases that are found in these structures, are purine and pyrimidine. And in DNA, we have adenine, guanine, cytosine, and thymine. So this is for DNA. Let's put a little asterisk down here. And then for RNA, these will switch out, and uracil was what you find in RNA. And the thing about the adenine and guanine and cytosine and thymine that's important is those are the base pairs, A, T, G, and C. So this pairs with that, and this pairs with that, that create the hydrogen bonding that allow the double helix sort of to stay together. Aside from proteins, where we see three different amine heterocycles, and then in DNA, we also have in our blood what's called a porphyrin ring system. And so this is heme when you insert the iron in the center of the nitrogens. So you deprotonate the hydrogens, and then an iron will come in and sit in the middle, an iron 2 complex in our blood that's responsible for transporting oxygen to the various parts of our body. This is very similar also to chlorophyll, and so it's still this little image from Wikipedia. And keep an eye on the porphyrin ring or the heme ring to chlorophyll, and you'll see in chlorophyll we have the porphyrin ring, and the thing that we've substituted in the middle is a magnesium. So heme, a nitrogen heterocycle, is found in a number of different ways in both our systems and plants. So that kind of brings us, oddly enough, to the end of organic chemistry. And we've covered the 4 different groups that Bruce outlines in her textbook. And so there's a nice little summary at the end of the chapter, and you should go back through and look at that, talking a lot about what the group 4 molecules have in common.